Thank you, Michael. Good afternoon, ladies and gentlemen. My name is Dmitry Sklyarov. Now I'm employed as lead analyst at Russian-based company Positive Technologies. And I will deliver you a short presentation, 30 minutes only, about flash storage forensics. First of all, what's flash and how we start using it? Actually, for many years, we used magnetic recording for most of types of data we are stored. It was invented more than 100 years ago and still used every day. A lot of hard drives still in use, and during years of using magnetic recorders, drives become smaller and smaller. But even if they become as small as on this picture, it's real drive produced in 2005. The technology almost the same like 100 years ago. The same general principles. When you deal with magnetic recorder, you could modify any piece of data almost independently from each other. So usually disk is divided on multiple sectors, but it's just for synchronization, for easily accessing, precise accessing data. Physically, we could address any tiny piece in almost in any sequence. So we could modify data as we like. And for many years of usage of magnetic recording devices, industry studied how to properly work with them and how to handle sensitive data that's stored on magnetic drives and how to destroy that data. And there are data erasure standards exists that allows people make sure that the data never would be able to read by anything else. Actually, not many people use that standards way they need to delete data, and there are many research about that published already. But several years ago, in actually 1948, a new technology came to our life called flash. It was invented by some Japanese guy, I believe. And in 1988 and 1989, two companies produced first commercial samples that were available for public that work with this principle. And they have two types of memory, an OR and an AND. They are based on two different types of logical elements, not OR, not AND. But actually, there are not big difference between them in the view of my presentation. Flash storage is electronic device, so no moving parts, no mechanics, no magnet fields involved, and it's store electric charge. Somehow it's complex physics. I really don't understand how it works. I studied electronics for a short time, but not enough. And modern technologies say that data stored in flash memory could be available for reading at least 10 years, and some samples allows you to read data up to 100 years after it was written inside the flash. And several words about the theory, what's the property of the flash, how it actually works. It's very different from magnetic drive, from common magnetic record. Yes, we could write any bit independently. So we could modify any piece of data independent of each other, with one exception. We need to erase data before we rewrite it. So there is no just modifying 0 to 1 or 1 to 0. We could easily modify any one bit to 0. But to return back to one state, we need to perform erase. And erase performed not per bit, not per byte, but per block. And block is usually several kilobytes. So to erase single bit, you need read data from all other bits from the whole block, erase that block, and write all bits back. So it's not very good idea to perform such slow operation. So some optimization algorithms involved, and I will talk about them a little bit later. And another big difference of flash memory in comparison with magnetic drive is limited number of erase cycles. With magnetic drive, with modern, good, high-quality magnetic drives, you could rewrite the same sector a huge amount of times, and it still work fine. So you will have no problem with reading or writing data to that sector. With flash drive, you are limited to small number of erase cycles per block. So if block erased, for example, for bad flash 10,000 times, you will never able to get all ones, all bits set in one state after erase. So that block considered to be bad, and it should be excluded from later usage. Good devices, good types of flash increase the number of cycles to million. But actually, when operating system like Windows work with file system, it's rewrite some sectors very often. For example, when you access to some directory, to any file on that directory, you need to update data about last access time. So every access could lead to write cycle and probably to erase cycle. So this problem makes using of flash completely different from hardware point of view. Flash memory usually divided in several banks, physical chips, and every chip have multiple blocks inside it, and every block have multiple page. For ease of usage, page usually divided in two parts. Data part, which should represent user data, and so-called spare part that could be used for storing some additional information that is necessary for properly handling everything that happens with flash. And usually there are three types of data could be written in spare area. It's information that some page or the whole block already broken, so it could not be erased anymore. Also, there could be information about error correction. Some types of flash use error correction for ignoring, for example, one bit erase error. So if you have only one wrong bit in page, you could still use this page using error correction algorithms. And sure, this spare area could be used for holding physical to logical mapping information, because there are some mapping layer due to physical properties of flash, because we can't write on the same sector every time we need to modify it. And here where the weird leveling algorithms comes. That algorithms, they aimed to make average leveling, average wearing of the whole flash on the same level. So every page of flash in ideal conditions should be erased equal number of times. It doesn't matter which logical page you are trying to access for writing, the average number of erase cycles should be evenly distributed over the whole flash. And if you achieve that goal, the flash will serve you as long as possible. If you make these algorithms more primitive, flash will be destroyed by erasing much sooner. So that algorithms, it's dynamic process. When your flash is connected to flash controller, something happens inside the flash. So it's trying to optimize which page to erase, which page to remap, and algorithms usually very complicated. It's developed by flash manufacturing companies, and usually it's not public. There are several public implementations for weird leveling algorithms, but nobody which algorithms exactly is used by Intel, for example. It's kind of trade secret. And several words about logical characteristics of flash devices. There are two types of devices. First type is usual USB flash drives that connected to USB port. It's a solid state drive. It's cards that's inserted on your photo camera. Mostly they are trying to represent your virtual hard drive. So you have logical access by sector level. So you need to know only number of sector you want to read or write. Everything, all mapping is performed inside the device, inside the flash card or inside USB drive. There is special controller that responsible for doing such operations. And from user point of view, it's all inside device. For solid state drives, people decided that it's good idea to say to controller that some page is not used anymore because file was deleted from the file system. So if you work with operating system that aware of using of solid state drive, there are a new command involved called trim command. When you erase some file, the logical sector that belongs to that files earlier is now not used at all. For sure, you could write some data to it, but actually, from the view of file system, that sector is empty. There is nothing useful inside it. And file system driver reports to flash controller that logical page with some number is not used anymore. And flash controller remembers this information, and after that, when you're trying to read this page by its logical number, controller or reports all zeros or just report there is no such sector available. So it seems that from forensic point of view, from extracting data, new technology, flash technology, trim command allows you to erase data such way that it's impossible to read. Another type of flash devices is embedded devices. Here is main board from, I believe, iPhone 4S. So during development of that type of devices, manufacturing companies, they already knew that they will deal with flash, and usually they not embed additional flash controller that handle like controller inside your flash drive or a flash card for the camera. They use some interface from central processor to flash memory and handle all weir leveling algorithms and all stuff that's related with mapping between logical to physical pages. They handle it inside the software, inside the firmware that run on that device. And using that knowledge that you are working with flash, it's much easier to optimize usage of flash memory and force it to work longer and reduce number of erase cycles and so on. This level between logical and physical pages, between number of sector and number of physical pages where the sector is stored right now, it's called flash translation layer. And when you turn on your device, for example, iPhone, it's read information about mapping from flash, hold it in memory during all operation time, and perform fast mapping for any requested sector you want to read from the flash. When you turn it off, all current mapping store it in flash again in some new page of flash and correctly closed. If you turn off your device physically, for example by disconnecting its battery, information about mapping is not complete. So you will need additional time when you're turning on the device before operating system loaded to collect information about proper mapping. There are such algorithm exists inside the firmware usually to represent flash as integral device without errors in mapping. And using flash translation layer, it's possible to report to flash controller that some page is not used, so send dream command. So some logical page number would be not mapped at all. And several words about what's happened when you are trying to modify some data. Old erasure standards for magnetic drives usually say that to erase data on some sector, you need to overwrite it multiple times with some templates or some random data and so on. What's happened when you just overwriting some logical sector on flash drive? Actually, as I said earlier, you can't write on the same page because to modify data on that page, you need to erase whole block, but that block holds some other useful information, and you need to remap that information to some other pages, or you could just not remove information right now. You could just allocate a new page that not used yet and change mapping. So the same logical number will map to other physical page. So during first writing of some sector, for example, physical page number 1 was used for storing that data. After you write again, new page with almost random number. Number is defined by flash translation layer, by varying leveling algorithms. New page is chosen, and now mapping point from the same logical page to absolutely different physical page. But previous version of data that was stored on flash, it's not erased. It's probably in the future would be erased by garbage collection algorithms or by remapping algorithms if you have lack of free space and need to use erased page again. And actually, in most cases, you can't predict when it's happened. So you have no control on how to force the flash controller to erase some specific physical page that in past contains sensitive data you want to erase. And actually, I start thinking about flash during research on iOS kernel, on what's happening inside it. And it's was figured out that flash translation layer on iOS devices implemented in the firmware. So if you knew how to look inside the Apple firmware, and it's not a big secret, there are many open source projects exist on that subject. So you have chance to see what the algorithms are used with flash, and you could try to figure out how they work. And for iPhone, for example, and other iOS devices, spare data of every flash page contains actually two significant values. First value is logical page number, so the number of logical page that maps to this physical page. And another number is update sequence number. So when you write in flash for the next time in any page, this number is increased by 1. This is true for iPhone 4 CDMA model. It uses some recently invented, or I don't know how to say, ordered by Apple, a flash type called PPN, Perfect Page New. So it's a kind of flash type that guaranteed that there would be no physically broken pages. I don't know how they achieve that, but there are no bad pages on that flash from the point of view from flash controller. So when you have information about logical page number and about sequence update number, you could just build mapping for any logical page to multiple physical pages in correct order. So you could find multiple states of some logical page. And that page will be ordered in time. And I believe it's very big achievement from point of view from forensic point of view. when you could find how this file was changed during time, you could get additional information. Unfortunately, not every page stored in multiple states, and some pages are stored in single state, last one, because previous copies was erased with garbage collection or remapping. But anyway, you could build the history sometimes. And several words about how to access flash controller at the lowest level. For sure, operating system have that access, and kernel have way to read the controller. And there are kernel service available inside the iOS that responsible for dealing with user-level applications that allows to read and write pages on the flash. And that level was found in iOS 3 and iOS 4, but in iOS 5, Apple decided to strict people who want to abuse it, and they just remove support for read and write requests. So the kernel service still exists. It have external methods, so you could call it, but you could call it for obtaining flash geometry. You could find what's the number of banks, number of pages, number of bytes in spare area, and so on. But you are unable to read pages. But there are at least two ways exist how to bypass this limitation. First way is to load your customized kernel from previous version of iOS, for example, iOS 4. Probably you will have some problem with file system at logical level, because there are some improvements in iOS 5 and iOS 6 relative to iOS 4. But you will have the same level of access to flash. So you could just read data using old version of operating system. And another approach, you could just modify kernel in memory to force it re-implement the read capability. And after that, again, you will be able to read that data. And in RAM disk that distributed with iOS firmware updates files, IPSV, in some versions there are client-side application exists, client not in term computer and mobile phone, but in term kernel and user. In user level applications that issues request to external method of your flash controller user client and reads data. So you could find samples how to do it, how to work with this service. And this technique allows people to get content of flash from old A4 devices. It's old iPhones prior to iPhone 4 and first iPad and first fourth generation of iPod. So it's old version of bootloader allows you to load custom kernel and run any application you like. So you have ability to get access to this type of the phone. If you jailbroken your own device or owner of the device jailbroken it, again you have chance to modify kernel in memory, and again you could read all data from the flash, but sometimes you have problem because it's conflict with running operating system and just reboot the phone, so you need to try how to force it work. And for sure, if you're Apple or have good relationship with Apple, for example, you are US government, you could ask Apple to sign your RAM disk and load your kernel and run your program that will allow you to read the whole dump of the flash. It's slow process for 64 gigabytes devices. It takes maybe 5-6 hours to read the whole flash. But it could be done. You need just computer and cable for iPhone. And several words about how forensic it. Forensic is part of criminalistics that search for proofs for the court. So there are general approach for forensics is extract as many evidences as possible without modifying the source of the evidences. Unfortunately, it's not too forensic because when you turn on your phone, even without loading operating system, flash controller starts working and some remapping already could occur. So you couldn't stop this process. Actually, you could open the device, unsolder the flash chip, but in this case, you will need to face another problem. All modern models of iOS devices use hardware-based encryption, and all data stored on flash is encrypted. So you could get data, but all of that data would be encrypted. And you need to get encryption key, and that key is embedded in processor, so you couldn't read the key value. You could just run code on processor that perform operation with that key. So probably if you desolder the flash, you will not succeed anyway. But when you perform reading of the same device twice, you will get different results. Not completely different, but multiple pages would be remapped between two attempts of read the data. And the main question is there a secure way to erase your data from the flash on such type of device? And personally for me, I still have no right answer. I'm not sure. As I see from the algorithms, the more your drive is filled with data, so the less amount of free space, the faster data are rewritten to, with erasing the whole block. But for example, with some iPhone 4 that was just used for testing, I find 4 different copies of the partition map. So of the first sector of the file that not belongs to file systems, that holds information about which parts of flash storage belongs to which logical partitions. And by analyzing that for versions, I could figure out what mapping of space was used during installation of the operating system. So you could just follow the logic of the installer just by seeing 4 different versions, because a lot of free pages left on the device and there was no need to rewrite them. Probably you knew that modern Apple devices have ability to remotely wipe all data, and they did it not by wiping every page on flash. They wiping only one significant part, that is encryption key. It's randomly generated when installing operating system, and after you erase it, you will be unable to read all data. And to avoid such situation when by erasing key you actually not removed it from flash, Apple map some part of flash to special area called effaceable storage. It's not controlled by general algorithms of wear leveling. It's handled in other way, and there are special part of iOS code that use it to remove all data from that part. So no unmapped pages, no pages that have a previous version of that key will exist after erasing. So Apple think about it because in iOS 3 they left, they hold key in the last sector of the logical partition and erase it. But it's still preserved in some page of, some old copy of some page. So I don't know how to erase flash properly. By reinstalling operating system on Apple device, you for sure destroy the encryption key, so nobody will be able to decrypt all your data unless he already have your key. For example, if he examined your device before. But still open question how to do it from software layer. So what commands you need to issue on your device to erase the data. And I need to mention Elcomsoft, my former company I worked for, and part of this research was performed during my employment in Elcomsoft in cooperation with Andrei Belenko. I need to mention guys from Sogeti. Actually, they made perfect research almost in the same time like me and Andrei in last summer, and they published its results. So if you need some details or even code that personally me was unable to compile, you could just visit their site, read their article about low-level access to iOS devices, and probably you will find additional information on this subject. And I want to thank the Troopers Conference and ERNW for the chance to present you my research. And thank you for listening. If you have any question, I'll try to answer. Thank you.
Thank you, Dmitry. I think one of the most important questions was already answered, because I think many people are interested how to wipe or delete the flash memory in a secure way, but okay, we still have to wait. Are there other questions about the topic? Looks like everyone is... wait, Mike.
Thanks a lot. Where is the mapping table stored, and how is that not overwritten or erased too many times?
Actually, mapping is stored in two parts. First part is USN and logical page number, update sequence number, and logical page number that's stored in the spare area of every page. So by reading the whole flash, you could rebuild that information. And also there are special pages called master blocks. There is algorithms of finding such pages, and they are remapped too, and that area is used to store nowadays just correct information about flash mapping. When you turn your device off, that information is updated, and next time you boot it, flash controller not use it to read the whole flash, it's just find the last opened master block and get all information from there. So that block is treated as usual block, so it could be erased again if you need to free space, and every time you perform synchronization of the mapping tables, you just choose new free block and store information there. So it's dynamically placed in flash, but with some limitation.
Okay, other questions? Okay, doesn't look like so. Dmitry, thank you very much.
Okay, thank you.